Hello and welcome to this lecture. We are studying chapter 7, 7.1, functions. Officially, we define a function like f, which is a special type of a relation, map set x into second set y. X is the domain, y is the codomain. This special type of relation must satisfy two conditions. The first condition is every element in the domain X is related to some element in the codomain Y. Second of all, no element in the domain is related to more than one element in Y. Remember that this condition is nothing but passing vertical line test. So this is just passing vertical line test in algebra. Exact same meaning. Thus, given any element like X in the domain, there is a unique element in Y that is related to X by F. If we call this element Y, then we say that F sends or maps X to Y. And we write F maps element X into element Y. The unique element to which F sends X is denoted by F of X. And it's called F of X, the output of F for the input X, or the value of F at X. Or you can also say that F of X is the image of X under F. The set of all values of F taken together is called the range of F, or the image of X under F. We can write it this way. Range of F is equal to image of X under F, which is equal to the set of all Y values in the codomain such that Y is equal to F of X for some X in domain X. Given an element Y in Y, there may exist elements in the domain X with Y as their image. If F of X is equal to Y, then X is called a pre-image of Y or an inverse image of Y. Guys, note that it's not inverse. For an inverse, the function must be 1-to-1. It must pass horizontal line test. That's why we call it inverse image. The set of all inverse images of Y is called the inverse image of Y, and we denote it this way. The inverse image of Y is the set of all X values such that F of X is equal to Y. If we have finite sets, if we have sets that we can actually count the elements, it's easier to use arrows to represent a function. This is called arrow diagram for the function. So recall that if X and Y are finite sets, you can define a function like F from X to Y by drawing an arrow diagram. You make a list of elements in X and a list of elements in Y, and then you draw an arrow for each element in X to the corresponding element in Y. So for example, this function maps X of 1 into Y sub 3. It maps X sub 2 into Y sub 1. It maps X sub 3 into Y sub 3, and it also maps X sub 4 into Y sub 4. So as you can see, there are elements in the codomain Y which are not mapped to any element in the domain X, and that's absolutely fine. Example, functions and non-functions. Which of the arrow diagrams in the figure below define functions from X, which includes A, B, C, to Y, which includes 1, 2, 3, 4. So the first one maps A to 1. It doesn't map B to anything, so it's not a function. The second one, A to 1, B to 2, it also sends C to 2. Remember that if it's a function, it must map C to a unique element. So B is also not a function. Take a look at C. It maps A to 3, it maps B to 1, it maps C to 3. So they're absolutely fine. Even though this is not a one-to-one function, but it is a function. Another example, consider this function like f that maps a, b, c into 1, 2, 3, 4. This is your domain and y is the codomain. Suppose we define a function this way. This function maps a to 2, b to 4, and c to 2. Question says first write the domain and codomain of the function. The domain of the function is the set including a, b, c, and codomain of the function is the set including 1, 2, 3, 4. The range of the function is just 2 and 4. B, find f of a, f of b, and f of c. As you can see, f maps a to 2. So f of a is equal to 2. B is mapped to 4, so f of b is equal to 4. C is mapped to 2, so f of c is equal to 2. What's the range of the function? The range of the function includes 2 and 4. So range of f is the set including 2 and 4. D, is C an inverse image of 2? Take a look at C. C is here. 2 is here. C is mapped to 2, so inverse image of 2 is equal to C. So the answer is yes. Is B an inverse image of 3? Take a look at B. B is mapped to 4, so B is inverse image of 4, not 3. So the answer is no. E says find the inverse images of 2, 4, and 1. Inverse image of 2 is A and also C. So the inverse image of 2 is the set including A and C. That's why we use curly brackets here. The inverse image of 4 is one element, B. Don't forget to write it in a set symbol. And the inverse image of 1 is not attached to any element in the domain, so it's going to be empty set as the inverse image of 1. F says represent function f as a set of ordered pairs. We know that any function is a collection of points in xy plane with those conditions, so we can represent the function using the collection of ordered pairs. A2, B4, C2. This is your function. It passes vertical line test. It doesn't pass horizontal line test. So it's not a one-to-one function. Theorem. A test for function equality. Suppose you have two functions, f that maps x to y, g that maps x to y. Then function f as a collection of ordered pair. Collection of ordered pairs is equal to function g as a collection of ordered pairs if and only if f of x is equal to g of x for all x in the common domain x. Let us prove this. Suppose f and g are functions, and also f is equal to g. Your goal is to show that f of x is equal to g of x. Very well. F is equal to g. F is a collection of ordered pairs. G is equal to a collection of another set of ordered pairs. Two ordered pairs are equal to each other if and only if their first coordinates are the same. The second coordinates are also the same. So f and g are relations from x to y, and they satisfy the two additional function properties. F and g are subsets of Cartesian product x and y. So for any point xy in f, it means that y is a unique element related to x by f, which we denote by f of x. At the same time, x and y as a point in ordered pair set G, it means that G maps x into y, which is unique element related to x by G, G of x. So suppose that f of x is equal to g of x for all x belongs to x, then if x is any element in x, x and y as a point is in f, if and only if x is connected to y through f, or y is the image of x under f. At the same time, we know that y is a unique element. So this unique element must be equal to g of x by the explanation here. What's the meaning of that? It means that the point x and y belongs to g. So f and g as collection of ordered pairs consist of exactly the same elements, and therefore you can conclude that f is equal to g. Conversely, if f is equal to g, two collection of ordered pairs are equal to each other, then y equals to f of x. The meaning of that is the point x and y belongs to that collection of ordered pairs. What's the meaning of that? Since f is equal to g, these two sets are equal to each other, so you can interchange these two. X and y is an element in g. What's the meaning of that? It means that y is equal to g of x. Y is the image of x under g. So since f of x and g of x are equal to each other, for any x in x, you can say that f of x is equal to g of x. Definition of identity function. Suppose x is a set, I sub x is a function that maps x to x. It takes any element in x and map it to the same element in x. We call this function an identity function on x. What's the use of this function? We use this function for the purpose of composition of a function with its inverse. If a function is one-to-one, then it has an inverse. The composition of any function with its inverse is equal to identity function. One important concept is being well-defined. So when you define a function, you always have to check to see if it's well-defined or not. What's the meaning of that? In general, we say that a function is not well-defined if it fails to satisfy at least one of the requirements to being a function. Let us take a look at one example to see what's going on here. Do we have a function that is not well defined? Okay, consider rational sets of rational numbers. And suppose you read the function like this. You say that, hey, I have a mapping like f that maps rational numbers into integers, and I want to define it this way. I say if I take a fraction m over n, this mapping maps this fraction into its numerator m. And suppose the denominator is never 0. Okay, do we have a function? Does this mapping satisfy all the conditions to be a function? The answer is no. Why? Take a look at two fractions, 3 over 6 and the reduced form of 3 over 6. These are just x values. If I leave the fraction as it is without reducing it, the function f maps 3 over 6 into 3. If I reduce the fraction to 1 over 2, f of a half is equal to 1. But as you can see, the y values are not the same. X values are the same, but y values are not the same. So this mapping is not a function. Functions acting on sets. Suppose you have a function that maps x to y, then you can consider the set of images in y of all the elements in a subset of x and the set of inverse images in x of all the elements in a subset of y. Image of A under F is equal to all the y values in the second set such that y is equal to f of x for some x in A. Inverse image of C under F is the collection of all x values such that f of x is a member in C. Also note that if you take y in y, inverse image of y is equal to inverse image of set of y. Let's take a look at one example, see what's going on. The action of a function on a subset of a set. Suppose x is 1, 2, 3, 4, y is a, b, c, d, e, and you define a function to be like this. We use arrows to define this function. Suppose x, 1, 2, 3, 4, has some subsets. A is a subset of x, including 1 and 4. C is a subset of y, including a and b. D is a subset of y, including c and e. Find f of a, f of x, inverse image of c, and inverse image of d. Okay, f of a includes 1 and 4. 1 is mapped to 2, 1 is mapped to b, and 4 is also mapped to b. So f of a is the set including one element b. F of x. X includes 1, 2, 3, 4. 1 is mapped to b, 2 is mapped to a, 3 is mapped to d, and 4 is mapped to b. So f of x, the image of x under f, is the set including a, b, and d. Note that here we defined the range of the function. Now, C as a subset of y, inverse image of C. Okay, C is A and B. A is mapped to 2, B is mapped to 1, and also 4. So inverse image of C includes 3 elements, 1, 2, and 4. Take a look at D. D includes C and E. C is mapped to nothing. E is mapped to nothing. So inverse image of D is empty. Example. Suppose you have two sets, x and y, and f is a function that maps x to y. Suppose you have two subsets of x. Then the image of A union B under F is a subset of the union of their images. We have first set to be the subset of the second set. To prove that, you need to take a random element in the set on the left-hand side and show that that element lands in the set on the right-hand side. So take a random element. Y belongs to the image of A union B. What's the meaning of that? It means that there is some element like X in the union A union B such that f of X is equal to Y. X is in A union B. What's the meaning of that? It means that X is in A or X is in B. If X is in A, you know that Y is equal to f of X. Therefore, Y belongs to image of A under F. So, since Y belongs to f of A, Y belongs to f of A union with any other set. Here you can write f of B. Case 2, if X is in B, it means that there is an element X is in B such that Y is equal to f of X. That's the definition of our function. Function f maps X to Y. So Y belongs to f of B, the same argument. Since Y is a member of this set, f of B, Y belongs to any other union. So using these two cases, we showed that Y lands in the set on the right-hand side.